All right, so on Tuesday, we had started looking at the chi-squared distribution. And the chi-squared distribution is used in for two different things. The first thing that we looked at on Tuesday, in which we are going to look at in this example, is the test to see if what you get, what you observe, is what you would expect. So in this experiment, we're flipping a coin. And we flip it 100 times. And what we see is that we get 20 heads. 27 of the flips are the first coin's a head, the second coin's a tail. 30, the first coin is a tail and the second coin is a head. And then we get 23 flips that are both tails. So what we observe from our experiment is 20 heads, 27 head tails, 30 tail heads, and 23 tail tails. Now, what would we expect? Theoretically. So the probability of you getting a head and a head, if you remember back in probability, whatever chapter that was, these are independent events. Flipping the second coin, whatever happens with the first coin doesn't affect the second coin whatsoever. So since these are independent events, you multiply the two probabilities together. Okay, so if you flip a coin, the probability of you getting a head is 1/2. The probability of the second one being a head is also 1/2. So the probability of getting two heads is 1/4. Well, that's true for all the rest of those. So the probability of getting a head and a tail would be the probability of getting a head times the probability of getting a tail, which would be 1/2 times 1/2, which would be 1/4. And the probability of getting a tail and a head would be the probability of getting a tail times the probability of getting a head, which again would be 1/2 times 1/2. You see where we're going here, which was 1/4. And the probability of getting two tails would be the probability of getting tail times the probability of getting a tail, which would be 1/2 times 1/2 times, which would equal 1/4. So if you flip a coin 100 times, you would expect 1/4 of them to be head. So you would expect 25 would be heads. You would expect 1/4 of them, 1/4 of them to be head tail. You would expect theoretically that 25 of them would be tail heads and 25 of them would be tail. So that's what you would expect to see theoretically if the coin is balanced. Okay, so now we're going to use the chi-squared distribution to determine if what we observed is significantly different than what we expect. Okay, so when we do the chi-squared distribution, we have to have our categories to be numeric. Okay, so we're not going to be able to draw a table over here using categories. And our categories being head, head, tail, tail, head, and tail, tail. We can't do that. We need our categories to be numeric. So we need to decide what we're going to look at. So what I'm going to look at, you could do it either way. You could do the number of heads or the number of tails. Either way, you're flipping two coins, you got a head, you got a tail. So I'm going to count the number of heads I get versus the number of tails I get. So I can't do it this way. What I'm going to do is the number of heads. Okay, so I can get none, I can get one, or I can get two. Okay, so what I observed is I had 23 that were no heads. I had 57 which were both, excuse me, one, and I had 20 which were two heads. Okay, what I would expect is this would be 25, this would be 25, but I would get 50 of them that would be one head, because I have 25 that are head tails and 25 that are tail heads. So I would expect, oops, and I just wrote 25. I would expect those to be 50. Okay, so the degrees of freedom here, the categories I created, there are 3 of them, 0, 1, and 2. So that's 3 minus 1, which is 2. Okay, so our null hypothesis would be that the coins are fair. That's what we're looking at, or they're not. The coins that I'm using in this experiment are fair or they're not. Okay, so again, I need to figure out the Pearson residual. This would be pretty easy to do by hand, or I can go put this data in my calculator. I can put the observed in L1 and the expected in L2, and then run the chi-squared goodness of fit test. And it's kind of, 6 of one, half dozen of the other. This is a pretty easy one to do by hand to calculate the Pearson residual. You take the observed minus the expected, you square that, and then divide that by what you expect. I'm just going to go put it in my calculator because I'm lazy. So I'm going to go to my calculator and I'm going to go to my lists, and I have no idea what's in there. Stuff. So I'm going to clear it out. Okay. So in L1, I'm going to put what I observed. Oops. So no heads, there were 23. One head, there were 57. And two heads, there were 20. And what I would expect is 25, 50, and 25. Okay, exit out of here. Go to stats, tests, find the chi-squared goodness of fit, which is D. I'm going to use L1 and L2. Degrees of freedom is 2. Okay, so looking at this, my p-value is 0.3, which is considerably larger than my preset alpha. So I can't reject the null hypothesis saying that these coins are fair. So my sample data does not support the idea that these coins are not fair. They do appear to be fair. Since alpha is less than p, we do not reject the null hypothesis. There is insufficient evidence to conclude that the coins are not fair. Okay, and that is our goodness of fit. The next way we use the chi-squared is a test of independence. And we're going to be using contingency tables in this section. And we're going to use matrices in our calculators. All right. So test of independence involve using a contingency table of observed data values. The test statistic for a test of independence is similar to that of a goodness of fit test, but you'll notice you're summing over I and J, which are the number of rows and the number of columns in your table. So O is your observed value, E is what you would expect, I is the number of rows in the table, J is the number of columns in the table. There are I times J terms of the form O minus E squared over E. The test of independence determines whether two factors are independent or not. The degrees of freedom in this test is the number of rows in your contingency table times the number of columns, the number of rows minus 1 times the number of columns minus 1. And just to remind you, we just talked about this just a minute ago, what constitutes two events being independent. They're independent if one event in no way, shape, or form affects the other event. And for example, we just looked at rolling two or tossing two coins. Whatever the second coin, whatever comes up is completely and totally independent of what's on the first coin. And the outcome on a roll of a die, the first roll does not in any way, shape, or form affect the value on the second roll. Those are independent events. Just as a note, this is similar to our test for goodness of fit. Each cell in your contingency table must be at least 5. If it is not, you need to combine categories. Okay, so here we go. Suppose A is a speeding violation in the last year, and B is a cell phone user while driving. If A and B are independent, so if getting a speeding violation is independent from using your cell phone, then the probability of A and B occurring is the probability of A times the probability of B. A and B is the event that a driver received a speeding violation last year and also used a cell phone while driving. Suppose in a study of drivers who received a speeding violation in the last year and who used cell phone while driving, that 755 people were surveyed. Out of the 755, 70 had a speeding violation, 685 did not, 305 were using their cell phones while driving, and 450 did not. So the probability of you getting a speeding violation and using your cell phone is, let's let Y be the expected number of drivers who used a cell phone while driving. So this is someone who was using their cell phone, they were driving, and they received a speeding violation. So if they're independent, the probability of A and B occurring is the product of the two probabilities. So the probability that you were using a cell phone while driving and received a speeding violation would be the probability of using your cell phone, which there were 70 out of the 755 surveyed, and times the probability of, get this right. So 70 had a speeding violation and 305 were using their cell phones. So 70 out of 755 are the number who got a speeding ticket, and the 305 out of 755 is the number of people who were using their cell phone. So if we take those two probabilities and multiply them together, we get the probability of both of those events occurring, an and probability. And if we multiply that by the number of people we survey, we take the probability and multiply it by the number of people surveyed, we get the value or the approximation of the people who were using cell phones and received speeding tickets. So about 28 people got both. And this leads us to how we find the expected values from a contingency table. Okay, so we took the probability of getting a speeding ticket times the probability of getting a using our cell phone, and we multiply that by the number of people surveyed. So we expect 28 people to be doing both. Okay. In a test of independence, we state the null and alternative hypothesis in words. Since the contingency table consists of two factors, the null hypothesis states that the factors are independent, and the alternative hypothesis states that they are not independent. If we do a test of independence using the example, then the null hypothesis would be being a cell phone user while driving and receiving a speeding violation are independent events. If the null hypothesis were true, we would expect about 28 people to use cell phones while driving and to receive a speeding violation. The test of independence is always right-tailed because of the calculation of the test statistic. If the expected and observed values are not close together, then the test statistic is very large and way out in the right tail of the chi-squared curve, as it is in the goodness of fit. The number of degrees of freedom for this test of independence is the number of columns in your contingency table minus 1 times the number of rows in your contingency table minus 1. And here is the formula for the expected value. You take the row total in your contingency table, you multiply it by the column total, and you divide it by the total number surveyed, which is what we did when we found the 28 in the previous example. Okay, so here we go. These problems take longer than any of them because of all the calculations you have to do. However, you can let your calculator do these calculations for you, and I'll show you what I mean in just a second. In a volunteer group, adults 21 and older volunteer from 1 to 9 hours each week to spend time with a disabled senior citizen. The program recruits among community college students, four-year college students, and non-students. In this table, there is a sample of the adult volunteers and the number of hours they volunteer per week. Is the number of hours volunteered independent of the type of volunteer? So does it make a difference if you are a community college student, a four-year college student, or a non-student, and the number of hours you volunteer? Okay, so this contingency table shows us the type of volunteer that we have and the number of hours that these volunteers work. We surveyed 839 people. That is this total. And you can see the numbers for each of the categories. For example, of community college students, 111, of the 839, 111 community college students volunteered from 1 to 3 hours. That's what that cell says. 53 non-students out of the 839 surveyed volunteered from 7 to 9 hours. So this table is our observed values. Now we must find the expected values for this example. Okay, so we have to find all the expected values, and there are going to be 9 of them that we have to find, because we have to find an expected value for each one of these cells, what we would expect. Okay, so to find the expected value, let's say of this first cell. Now again, this is what we observe. To find what we expect, we take the row total times the column total, and we divide it by the total. So the expected value for that cell, what you would expect, would be 255 times 298 divided by 839. Okay, so what's that equal to? I don't have my calculator out. Does anybody have the calculator out? What's that equal to? 255 times 289 divided by 839. I have the number here, but I want to make sure.
I got 90.57.
Perfect. That's exactly what it should be. Okay, so you've got one of two choices. I should say my null and alternative hypothesis. The null hypothesis would be that the hours that you volunteer are completely and totally independent of what type of volunteer you are. And the alternative hypothesis would be that they are not independent. Okay, so you got one of two choices here. The top table is my observed values. We're going to fill out the bottom table with what we expect. You can do this either using your calculator like you just did, or you can put this in your calculator and let your calculator calculate it for you. So for example, this first one was the 255 times the 298 divided by the total, which was 839. And you told me that was 90.57, which it is. Okay, so I can do that. I can fill this table out by doing all that calculation. Or I can put this table in my calculator. This is what we're going to do. We're going to put these two tables in our calculator. So how do we put a table with rows and columns in a calculator? We use matrices. So I need to find my matrix menu. First of all, I need to delete the matrices I have in here because we are in college algebra right now. We're doing systems of linear equations. And so how do they solve systems of linear equations? They use matrices. So I have a whole bunch of matrices in here. So let me show you how to delete a matrix once you get one in your calculator. So I go second plus to my memory. And I have all sorts of categories in my memory management, but I need number 2 because I'm going to delete matrices. So I go to number 2. And number 5 is my matrices. So I'm going to go to number 5. And you can see I have 5 matrices that I put in here this morning. So I need to delete all those. So I go to my delete key right here on my calculator and I just delete them. I have them all gone. So now I can go put my matrices in. Okay. So the matrix menu, do you all have a calculator? Do you have a calculator? Do you have a calculator? Okay. Just want to make sure because you really want to practice this on a calculator. So I'm going to go to my matrix menu. My matrix menu is found above the inverse button. Do you see that? That blue matrix up there? Above the reciprocal or index inverse button is my matrix menu. So if I go second inverse, there is my matrix menu. And I want to put a matrix in. So I'm going to go over to edit. Okay. And I'm going to edit matrix A. I am going to put the values I observed in this first matrix. Now let me go back over to PowerPoint. This matrix has 3 categories for the type of volunteer. So there are 3 rows. Community college students is row 1. 4-year college students is row 2. Non-students is row 3. So there are 3 rows. So the first number that I tell my calculator is the number of rows in this table. So we go back over here and we type 3, click 3 button and enter. And as soon as I do that, it creates my 3 rows. Okay, let's go back to our PowerPoint slide. In this observed data, I have 3 columns of the number of hours. So I have 1 to 3, 4 to 6, and 7 to 9. So I have 3 columns of data. So the second number I put into my calculator is the number of columns. And then I input those cells. Let me see if I can make this small enough that we can see both the table. And let's do this. The table, and I don't know if you've got that table written down. You might not have. The table and the calculator. So let's get this over here and see if we can blow it up a little bit and make it a little bit bigger. Maybe we can see that. Barely, but I can see it. Okay, so now I'm going to put these values into my calculator. It helps if you don't click off the example. Okay, So I'm going to put 11 in that first row, 111 in that first row, first column. So I'm just going to type in 111 and then enter. And then I'll move me to the second element in that first row, which is 96. And then the third element is that 48? See, I've got it so small, I can't see it. 48. Okay, so there's my first row in my table of observed values. Then we're going to put the second row in, 96, 133, 61. So there is the second row in the table of my observed values. Then we're going to put 91, and we're going to put 150 and 53. So there is the table, the matrix that contains the values that I observed from my survey. This is what people told me. So now I want to put the expected values in. So I'm going to exit out of this matrix. So I have to completely get out, do a second quit, and then go back in. It's the only way you can do this. I know it's very annoying. And now you can see that that table I put in is in matrix A. I'm going to go over and I'm going to put the expected values in B. This is also going to be 3 rows and 3 columns. All right, so now I either put this, I actually calculated all 9 of these cells. So I took my calculator out and I did 255 times 298, and I divided that by 839 to find that first cell. Or I can let my calculator do it. So I can type in 255 times, what was my row total? 298, and then divide that by the total, which is 839, and it calculates it for me. And I do the second, the first row, the second category, the 4 to 6 hours, the same way. The row total is 255 times the column total for 4 to 6 hours is 379. Oh, I got a plus. Should be a times. So 255 times 379 divided by 839. So we get 115.19. And we just continue in the same manner. So in the first row, the third category, 7 to 9 hours, the row total is 255. The column total is 162. We're going to divide that by the total, which is 839. Okay, and then we do the same thing for the second row. We have 290 times 298 divided by 839, 103. Then in the next category, we have the row total is 290. The column total is 379. We're going to divide that by the total, 839, 131. And in that next last category in that second row, the row total is 290. The column total is 162. Divided by the total, which is 839. This is the most work in these problems, believe me. Okay, so that looks good. And then we're going to do the last row. So we have 294 times 298 divided by 839. And then we have row total 294 times column total, which is 379, divided by total. And last but not least, we have the row total, 294, the column total, which is 162, divided by the total, which is 839. And there is my table of expected values. So I have my observed values in a matrix, that table, and I have the expected values in a table. So I'm going to exit out of my matrix menu because I'm done with putting matrices in for now. So now I'm going to go conduct the chi-squared test for independence. So I'm going to go to stat tests, and I'm going to find the chi-squared test, which is C. So this is the chi-squared test for independence. And when I click on that, you can see that it wants to know where I put the observed and the expected values. So to tell my calculator that the observed values are in matrix A, I go to the matrix menu, second inverse, and just hit enter. So now the observed values are in matrix A. I go down, the expected I put in B. So I go second matrix, number 2 is B. And now I can calculate the chi-squared test. The observed values I put in A, the expected values I put in B. So my chi-squared statistic is 12.99, and my p-value is 0.0113. And you can see that it calculated the degrees of freedom for me. How nice is that? Remember, the degrees of freedom are the number of rows minus 1. We have 3 rows. 3 minus 1 is 2. Times the number of columns minus 1. We have 3 columns. 3 minus 1 is 2. 2 times 2 is 4. Okay, so go back to our PowerPoint. Okay, so we got a p-value of 0.0113. And you might have noticed, or maybe you didn't, that this particular problem did not specify a specific alpha value. So since no alpha was given, we always assume 0.05. So the alpha is larger than the p-value, the p is smaller, p is low. So since the p-value is lower than the alpha, the p is low, the null must go. So we are going to reject the null hypothesis. This means the factors are not independent. The type of volunteer you are and the number of hours you volunteer are dependent on each other. So at a 5% level of significance from the data, there is sufficient evidence to conclude that the number of hours volunteered and the type of volunteer are dependent on one another. De Anza College is interested in the relationship between anxiety level and the need to succeed in school. A random sample of 400 students took a test that measured anxiety level and need to succeed in school. The table on the next slide shows the results. De Anza College wants to know if anxiety level and need to succeed in school are independent events. So here is the table that shows the data that they took from this test for these 400 students. So we have 3 rows. They have a high need to succeed, a medium need, or a low need. And we have 5 columns: high anxiety, medium high anxiety, medium anxiety, medium to low anxiety, or low anxiety. So we have a 3-row, 5-column table. And we're going to put this in our calculator, and then we're going to calculate the expected values. Now, it may be just as easy to calculate the expected values on your calculator and then put it in that way. All right, so what's our null and alternative hypothesis going to be? So this is our observed data. So our null hypothesis would be let's put that over here. Our null hypothesis would be that anxiety and need to succeed. Do you believe that this is independent? What do you think? Do you think that your anxiety level is independent of your need to succeed in college? I'm thinking not, but let's test it to find out. I may be wrong. One does not depend on the other. I'm thinking that's not true. So our alternative would be okay. So here is our observed values. Let's find our expected. Again, you can do this while you're putting in the matrix, or you could do it independent of that. You can be independent. So what would high anxiety, high need be? What would we expect? We take the row total times the column total and divide it by the total. So that first category, high need, high anxiety, would be 155 times 57 divided by 400. The next one would be 155 times 95 times the column total divided by 400. Let's put it down here. The next one would be medium anxiety, would be the row total times the column total divided by the total. Medium to low would be 155 times 63 divided by 400. And low would be 155 times 58 divided by 400. And you would continue doing this for all the categories in the table. Okay, so row total, column total divided by the total. All right, so what would we expect to see? I'm going to erase all this. That is this table here. So I am going to put both of these tables in my calculator. So it's going to be a 3x5 matrix, 3 rows, 5 columns. And you know, I might as well, I don't want to delete the 2 matrices that I just put in. So I'm going to put this in C and this in D. I mean, I don't want to delete those until I'm done completely with my homework. So I don't want to delete anything I put in there. Okay. So I need to get my calculator open and get this slide open. Hopefully I can see both of them well enough to do this. Get my calculator. All right. Let's see if I can, this old woman can actually see this. There it is. Grab that, move that out of the way. Make this a little bit bigger. All right. So I'm going to go to my matrix menu. I'm going to go over to edit, and I'm going to put that table that's the observed values, and that's the wrong table. Let's get the correct table in here. There we go. There we go. That's better. So let's put the observed values in matrix C. So I'm going to edit 3. There are 3 rows in this table. There are 5 columns in this table, 5 levels of anxiety. And I'm just going to input these numbers. And I'm pretty slow. You're probably a lot faster than me. I've discovered that it's actually faster on your calculator than on this emulator. So let's see. And I do want to stop once I get this all inputted to make sure that I've got everything correct, because one mistake is going to cause my test to be incorrect. Okay, so let's make sure I've got this in here correctly. It looks good. So there is the observed values. Now I'm going to go put this table that I created with the expected values in. So I'm going to exit out of here, go back into my matrix menu, go over to edit, and I'm going to put that in D. Okay, it's a 3-row, 5-column table. All right, so let's put this in here. So 22. Oops, see, I got it wrong already. 22.0875. It's like watching paint dry. And make sure I got that first row in there correctly. Okay, so I'm going to put the second row in. This is the hardest part of doing these problems, is getting this stuff in your calculator. and 27 point. Okay, I'm going to do a quick check of that second row. Okay, that looks good. Now I'll do the last row. I want to be sure and check before I run the test and hit submit on an exam that or hit enter on a homework problem. See, I got that one wrong, so I need to fix it. That I've checked all my data. See, I've got that one wrong. All right, let me check that real quick. Okay, the hard part's done. I've got all that data in my calculator. So now I'm going to go run the chi-squared test. So I'm going to get it out of my matrices. I'm going to go to stat tests. I'm going to find the chi-squared test. That's C. The observed values I put in matrix C, number 3 there. Enter. The expected values I put in D, number 4. Okay, and then we're going to calculate. And that is about as small a p-value as you can possibly get. What's that mean? Your need to succeed and your anxiety level are seriously not independent of each other. That is 0.0, there's 7 zeros in an 8, 0.708. That's an itty bitty teeny weeny p-value. So my skepticism was founded because I said, they got to be related to each other. They got to be. They cannot be independent. They've got to be dependent on each other, and they are. So go back to our slide. Oops, apparently I didn't have another slide. So our chi-squared statistic that we found was 48.42, but the p-value was 1, 2, 3, 4, 5, 6, 7, and an 8. That's very small. It's essentially 0. So the probability of these things not being related to each other is 0. They are related. One is related to the other. And that is the end of chapter 11. Are there any questions? We'll get you a little out a little early for Thanksgiving. Have a wonderful, quiet, restful Thanksgiving. Enjoy your families. And we'll see you on Tuesday, November the 30th.